Now we are going to discuss another procedure to find the turning points of a given function to deduce whether it is minimum, maximum, or a point of inflection. Look at this description. You can also find out whether stationary points are maximum points, minimum points, or points of inflection by finding the value of d2y over dx squared and, where necessary, d3y and dx cubed at stationary point. So when we find the stationary point, we calculate the derivative once more in order to calculate d2y over dx squared. This is because d2y over dx squared measures the change in gradient. If dy over dx equals to 0, so the first time we calculated it was equal to 0, that means we know that we have a stationary point. If we do the derivative once more and we discovered that it is greater than 0, then the point is a minimum point. We will know this without the need to construct a table. Just by calculating the second derivative and it is positive, then it is a minimum point. Okay, now if the gradient is equal to 0 and d2y over dx squared is negative, then the point is a maximum point. If the gradient is 0 and the second derivative is 0, then the point is either a maximum or a minimum point or a point of inflection. So here we didn't get an answer yet by using the second derivative to know the type of the turning point. In this case, you need to use the tabular method and consider the gradient on either side of the stationary point. We do this when the first and second derivative are equal to 0. Okay, now sometimes you may find the third derivative of this function. So dy over dx is 0, d2y over dx squared is 0, but the third derivative is not equal to 0. Then the point is a point of inflection. You may also see this notation, which is f double prime of x is the second derivative of the function f with respect to x, and f triple prime of x is the third derivative, and so on. So the number of primes defines the number of derivatives made on this function.